If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon for rice found at the site? Obviously, carbon here will use our same half-life we just used there, 5730, I think, was it? Years. All right, so see what you come up with on this one here. Okay, so let's take a look. Once again, we're still rolling with our first order kinetics here. And in this particular case, we do have the time given to us, which is 15,600 years. We have a living, which would be our initial. And again, this is a rate of radioactive decay, which is our counts per minute per gram of carbon, basically. So counts per minute per gram of carbon here. Really butchered that pretty badly. Let me try that again. So counts per minute per gram of carbon. We are looking for what the final counts here will be, our rate, basically. And once again, here we will need to use our half-life equation here to find our decay constant, which is what's missing. And since we just did it there in the last problem, we will use the same one, actually, since we're still using carbon in this case. And one of those days, let's try that again there. Natural log of 2 over 5730 years. So that gives us that same number there that we had previously for our decay constant 0.000121 reciprocal years. We are good in terms of the units of our decay constant and our time. They're both in years, so everything should cancel out correctly. So a little natural log of A equals the natural log of 20 minus 0.000121 reciprocal years, 15,600 years. Cleaning up the right-hand side there, going to get natural log of 20 minus 0.000121 times 15,600 years. Going to give us a 1.10813. Natural log of A, again, E in both sides there. Gonna give us a final rate here of about 3.03. The units here would be the same as the first one. These would be counts per minute per gram of carbon in this case here. Gram carbon. Any questions on that calculation? It is the final sort of calculation, right? So it should obviously, again, have a smaller amount of radioactive decay sort of coming off of it. So it should have a smaller counts per minute than our initial one. Any questions on first order kinetics and radioactive decay? Also, very common sort of variations is sometimes you're given percentages, and you can go in here with percentages as well. You know, if you had 100% of something, you go 100 and whatever the other percentage here, or you could do like 1 and point something on the other side. So you could go in with like kind of percentages. So sometimes they say like, you know, after it decayed and only 30% left or something like that. So obviously the initial would be 100 and 30 would be your final and stuff like that. So sometimes percentages are used a lot with this as well. Any questions on any of that there? All right, so continuing on here. We're gonna talk a little bit about fission, and a reminder that fission is basically the process where a nuclei will decay into two new nuclei usually. Also, usually give off some neutrons and also a lot of energy basically as well. This can be spontaneous, as we talked about at the beginning. It also can be helped along by shooting a particle at something and making it unstable, and this process will sort of start to occur. So during the process of nuclear fission, some of the mass of the nucleus is converted into energy. So the mass of the protons and neutrons that make up the nucleus, there's sort of a difference in the mass of the particles that make up the nucleus and really the mass of the actual nuclide itself or isotope itself. So some of that mass that gets converted into energy is what is sometimes referred to as the mass defect, and that is the little bit of mass that gets converted into energy. You could figure out that by using Einstein's equation, E equals mc squared, and c is the speed of light, and I'm going to roll with 3 times 10 to the 8 meters per second for that number. M in this case would be the mass defect here, and obviously that would give you your energy. As we talked about previously, something like uranium-235 that goes through a fission reaction will produce something like 1.7 times 10 to the 13 joules of energy. And if you compare that to like a really exothermic sort of chemical reaction where we're just breaking bonds and electrons, it produces something like 10 to the 6 joules of energy per mole. So an extreme amount of energy comes off in fission reactions. Like I said, that's why it's oftentimes used for, say, nuclear power sort of reactions, because it does give off a lot of energy as we are converting things in the nucleus, which requires some type of good energy overhaul to kind of change those guys. Now, that mass defect, as I mentioned before, is essentially that little bit of difference in the mass of technically the particles that make up the nucleus and what it forms. And a reminder that when we talk about nucleons, that is basically, the particles that are found in the nucleus, and that basically is your protons and neutrons, which is essentially your mass number when you think about it. Now, the energy that's released when a nucleus is formed is known as binding energy, and sometimes referred to as nuclear binding energy. And it is also, by the way, a measure of stability when we calculate the binding energy per nucleon. So if you calculate the energy per nucleon, the higher the energy per nucleon, binding energy per nucleon, the more stable it is. So this is another sort of measure of stability of something by comparing binding energy per nucleon. These are a couple of conversions that can allow you to just skip using Einstein's equation and just shooting off with these two, which are sort of based off of it. That's 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules, and 1 AMU of mass defect equals 931.5 mega electron volts. I would say in terms of binding energy per nucleon, there's 2 common units that are used, and that is joules per nucleon or mega electron volts per nucleon. So those are 2 common sort of units of nuclear binding energy that you would calculate. And again, like I said, you could go into Einstein's equation, you could kind of just use these conversions and sort of bypass it and stuff like that in a lot of cases. So let's take a look at one here together and sort of see how we could calculate something like this. So let's say we have an isotope of fluorine, it's fluorine 19, and it has a atomic mass of 18.9984 AMU. And we wanted to calculate the binding energy per nucleon. And the binding energy is the energy required to break up the nucleus into its components, protons and neutrons. And in this case here, what we would do is figure out the number of protons, and that should be equal to our atomic number, which means it's 9. We should also figure out the number of neutrons, which is the mass number in this case, minus the atomic number, which is 10. Now we could take the atomic mass of a proton and the atomic mass of a neutron, which for all intents purposes is most of the mass of the atom, right? Because a electron is like 1,800 times lighter than either one of these. So these are really the heaviest sort of particles that are present. So to figure out the mass defect, we would take the mass of our 9 protons that are there in this case. So we take 9 times 1.007825 AMU. We would add it to our 10 neutrons that are present. at a mass of 1.008665 AMU. And then we would subtract it from the atomic mass of the isotope in this case, which is 18.9984 AMU. And if we do that there, we will get 9 times 1.007825 plus 10 times 1.008665 minus 18.9984. That's going to get us something like 0.1587 AMU. So that is what is referred to as the mass defect. That is the difference in the mass of really the protons and neutrons that make up the nucleus and the mass, atomic mass of this particular isotope. So that slight difference is what's going to be converted into energy through this process here of fission. Now, at this point, you do have a couple of options. So I'm going to show you both so you could choose whichever way you like. Now, if we went with Einstein's sort of move here, which is our E is equal to mc squared, we would put our mass defect that we just calculated, 0.1587 AMU. We would take our speed of light, which is 3 times 10 to the 8 meters per second, and square it. And this would get us here 1.428 times 10 to the 16. The units that I have at this point are AMU, meters squared, seconds squared. So what I'm going to do is take that number, 1.428 times 10 to the 16 AMU, meters squared, seconds squared, and I'm going to divide it by, my friend, 6.022 times 10 to the 20. I'm going to go 6. And that would give me AMU per kilogram. That will cancel those out. That's because to the 23 is grams, right? So 26 would be kilograms, 3 over. And that's going to give me, if I do that there, 2.37 times 10 to the minus 11 kilograms, meters squared, seconds squared. Those units all equal a what? Equals a joule. Yeah, so kilogram, meter squared, second squared equals a joule. So our energy here, our binding energy, is 2.37 times 10 to the minus 11 joules, which we can then divide by the number of nucleons, which is 19 in this case, which is our protons and neutrons. And this will give us our binding energy per nucleon of 1.25, I'll call it, times 10 to the minus 12 joules per nucleon. Any question on that calculation? By the way, if I wanted to know how much mega electron volts that is per nucleon, which is another common unit of binding energy, I could just use the conversion we saw on the previous page for joules. And I'll take that and divide it by 1.602 to the minus 13. And give me something like 7.792 mega electron volts per nucleon. So that is the binding energy per nucleon. And again, that is also a measure of stability if you're comparing the two. First off, any question using Einstein's equation? Now, like I said before, if you kind of want to bypass Einstein's equation and you have access to those two conversions, which I would venture you might, you really could just pick it up with your mass defect here and roll with 0.1587 AMU You could use the conversion we saw on the previous page that an AMU is 931.5 mega electron volts. Take 0.1587 times 931.5 gives you 147.83 mega electron volts divided by 19 nucleons. Gets you about the same number, a little less with rounding, but in the same ballpark, mega electron volts per nucleon. And you obviously could then use the joules to get there as well. So you can go, either way and kind of use those conversions without using it, and it'll get you basically the same idea. A little slightly different there, I think, with some rounding that I did on the original number. Any questions on that? So this is the way that we could calculate our binding energy per nucleon. We figure out the protons, we figure out the neutrons, we subtract it from the atomic mass of the isotope. That gives us the mass defect that will be converted into energy through this process. Most of the time, we do ignore sort of electrons contributions. Sometimes books will include electrons in the mess, but really because protons and neutrons are 1,800 or so times heavier than an electron, a lot of times the electrons are sort of left out of the calculation as well. Any questions on that there? All right. Yeah. It will usually be given to you. So yeah, so that usually will be given to you in the problem, the mass of it. Yeah. Unless they give you the other information of like how many protons and neutrons, then you could, sort of figure it out. But usually that will definitely be given to you. That's it. Other questions? All right, so let's see here. Here's a graph, and as I mentioned before, the nuclear binding energy per nucleon is a measure of stability. And there's our friend right there, little iron 56 at the top of the nucleon per binding energy in terms of the height of it, and that would be your most stable sort of guy. So again, that is a measure of stability with our iron 56 being kind of at the top there. And in a sense, most stable nucleus will fall in between there. And again, fission or fusion is used to kind of bring everybody to that stable sort of arrangement. So why don't you try this one? Calculate the mass defect and the nuclear binding energy in mega electron volts. And why don't we do joules as well? Why don't we do them both? For carbon 16, radioactive isotope of carbon with a mass of 16.01470. Mass of, by the way, carbon is number 6 on the periodic table in case we forget. Protons mass again 1.007825 AMU. And neutron 1.008665. Okay, let's take a look. So once again here, we really want to figure out our protons and neutrons, how many we got going on. So obviously our protons here is going to be 6 for our atomic number. Neutrons in this case is, remember this is our mass number, so it's going to be 16 minus 6, which would be 10. So here our mass defect will be our 6 protons at 1.007825 AMU plus our 10 neutrons at 1.008665 AMU. Once again, we're going to basically subtract that from the atomic mass of the isotope here, which is 16.014701 AMU. A lot of numbers, 6.1.007825 plus 10 times 1.008665. And then we're going to subtract 16.014701. It's going to give us a mass defect here of 0.1189, I'll call it. I'll do a little rounding. At this point, again, you do have 2 options. You can definitely go into here. where again you take your mass defect, you do your speed of light, you then would divide it by Avogadro's number to the 26, and then that would get you joules if you want to go that route first. Alternatively, since it did originally want mega electron volts, we could just use that conversion factor that we saw on that previous slide, where 1 AMU mass defect is 931.5 mega electron volts. So we could do that there. And I'm going to take the non-rounded number on my calculator, giving me about 110.75 mega electron volts. We then can divide it by the nucleon, which is essentially the mass number, which is 16 in this case. And that would get us here about 6.922 mega electron volts per nucleon. Any questions on that part there so far? Since we did want joules as well, we can take this number here and use the other conversion that we saw on that slide, which goes from mega electron volts into joules. Obviously, if you went Einstein's equation, you get the joules up front and then convert to mega electron volts. Again, I'm going to use the non-rounded number here in my calculator to the minus 13. Would get us something like 1.1 times 10 to the minus 12 joules per nucleon. Any questions on either of those there? Oh. All right, let's take a look at one more here. And I think it's iron 56, actually. So let's take a look at that one. All right, so calculate the binding energy for iron 56 and iron right there, dead center. 26, I think. And we could do both again. We could do joules per nucleon and mega electron volts per nucleon. And the atomic mass of the isotope is the 55.93494 number. Okay, so let's take a look. Once again, here our protons should be 26, which is our atomic number. Our neutrons, mass number there, 56 minus 26 gives us 30. So we could calculate our mass defect once again by using the same mass as we used previously. So 26 times our proton mass plus 30 times our neutrons mass, all subtracted from the mass of the isotope here, 55,934.94 AMU. Gonna give us here 26 plus 30 times 1.008665 minus 55.93494, gonna get us here 0.5285. That's gonna be the bit of difference there, gonna be converted into energy. Once again, we can go with our conversion there of an AMU is 931.5 mega electron volts. Gets you 492.26 mega electron volts divided by 56 nucleon here. Gonna get us an 8.790 mega electron volts per nucleon. We also could use that conversion there once again to get to joules. And that was our mega electron volt, 1.602 times 10 to the minus 13 joules. And again, using the whole number, my calculator gets me about 1.4 times 10 to the minus 12 joules per nucleon. Any questions on that one there? Once again, you could also use Einstein's equation. And if you do, you would have kind of picked up with the mass defect, which was 0.528. Maybe I won't, or I'll just round a number there. What was that there? 4.6, I think. So 5285 AMU are 3 times 10 to the 8 meters per second squared. And that would get us there. If I find it, there it is. Times 4.756 times 10 to the 16 AMU meters squared second squared divided by your Avogadro's number to the 26 AMU per kilogram. Gets you 7.8979 times 10 to the minus 11 joules at that case divided by 56. And that should also take us to our same number pretty much of 1.4 times 10 to the minus 12 joules per nucleon. And obviously you could convert it at that point and go the other way. So again, it's up to you whichever way you want to kind of go. They both should kind of get you the same answer regardless of maybe slightly different again, depending on rounding that you do. Any questions on that calculation? Now, if we look at the three sort of isotopes that we calculated the binding energy per nucleon, we had our fluorine 19, which had something like 7.792 mega electron volts per nucleon. We had carbon 16, I think, that had 6.9 to 1 mega electron volts per nucleon. And we have our iron 56. And we can see in terms of stability of these three, the iron 56 should be more stable as it has a higher nucleon binding energy per nucleon, followed by iron fluorine 19. Lastly, here would be carbon 16 in terms of stability. So again, this is another sort of measure of stability that you could look at comparing the binding energy again per nucleon in this case. And as we saw in that graph, this was the guy that was at the top of the graph. As you can see, again, has the highest binding energy per nucleon. Any questions on that there? So let's talk a little bit about transmutation. And transmutation is sort of the idea, as I was mentioning before, you could kind of kick off, for example, fission reactions or just, these type of reactions by really sending a particle at a nucleus, and it gets a little upset when you shoot a particle at it. And you could use a particle accelerator to do that. It's got a magnetic field, electrical field, get the particle spinning, and then shoot it at your target, basically. And again, you can see these guys are bombarded here with some alpha particles, a proton, and it will make some different elements. This is essentially how we make those guys on the bottom there, the periodic table. All of our guys have all the names from, like, where they were developed and maybe who developed them, like americium, berkelium, californium, einsteinium, all these guys. Again, you can see pretty much most of these man-made sort of elements, if you will, do start with basically shooting a particle at a nucleus and sort of producing uh, the new nucleus, or sort of the man-made one. That's sometimes referred to as the transuranium elements, where all those guys 93 and above, where those guys sort of happen. This again could also happen in a fission reaction to sort of kick off the fission reaction rather than it being spontaneous. So for example, if you take something like a neutron here and you shoot it at a bowling ball, it becomes a bowling pin if it's very unstable. And then it will become two new nucleuses. It will also generate, again, usually several neutrons in this process of fission. The resulting sort of nucleuses that are formed there, for example, here, strontium and xenon, that's not always going to be the same nucleuses that are going to be formed as a result of this fission reaction. You can get some different combinations that will occur. But usually what definitely occurs is two new nucleuses, several neutrons, and a good amount of energy that basically happens here. We could calculate the energy again. This is the mass defect, which is basically the products minus the reactants here, and times it by our C squared, which is our Einstein's equation there. And we get something like, again, 2 times 10 to the 13 joules of energy per mole of uranium-235. And as we saw before, that is an incredibly amount of more energy, for example, that you get from, say, the combustion of coal, which is like 5 times 10 to the 7. The reason of these two comparisons is traditionally in a power plant, you either kind of burn coal or you burn or do a fission reaction. So you get a lot more energy in the fission reaction, say in a nuclear power plant versus a traditional coal-fired sort of power plant. As I mentioned before, you don't always necessarily get the same sort of fission products, but there are several sort of peaks in terms of mass numbers that do sort of come up, obviously, more times than not. But you don't always get that same sort of response. Now, this fission reaction, in addition to being used in a, say, nuclear power plant, is also sort of used in, say, something like a nuclear sort of bomb. And it can create a nuclear chain reaction. And a nuclear chain reaction is basically this fission reaction that basically just keeps going, basically. And the idea here is if you have the right amount of fissionable material, which is known as the critical mass, that's basically the mass that's needed of your radioactive guy that's going through fission, like uranium, to continue this reaction to keep growing. And because the fission reaction pretty much starts with like a neutron, and then it produces these new elements and more neutrons, that means these neutrons could just kind of keep coming on back and continuing this sort of project and reaction. So in a non-critical sort of situation where you have less than that, it will sort of be under control. It's not able to sort of propagate out of control, if you will. But if you do have the right amount of critical mass, every time you do that, you're making new neutrons. Every time we're getting energy and lots more radioactive products. And obviously it will continue to build and build. And it's sort of a nuclear bomb sort of situation. You have sort of the critical, subcritical masses of uranium-235 separated until it hits and explodes, causing them to kind of complete and make a critical mass of it, which would obviously continue that chain reaction sort of out of control. Now, we also use the same sort of fission reaction in, say, a nuclear power plant. And this is sort of a schematic of a nuclear power plant. Most power plants, traditional power plants, and nuclear power plants basically work the same. You usually got water, and you basically heat the water. Water that you heat makes steam. Steam goes out to like the turbine, right? And we get some lights and all that good stuff, right? And the nice thing about water is, or steam, you could cool it back down and you could get your water back. So a nice little sort of cycle that happens. The major difference between, say, a traditional power plant and a nuclear power plant is how they heat the water. In a traditional power plant, they burn coal and they use the energy from the coal to heat the water. In a nuclear power plant, they use a fission reaction and they use the heat generated from a fission reaction to heat the water and create the steam, which is what we see here. So this is obviously the part where the nuclear part occurs. And in there you have fuel rods, and these fuel rods are pretty much what it kind of sounds like. They're actually like little pellets of uranium, basically like eraser size of uranium little pellets. And it obviously will kick off this fission reaction. It has sort of a pretty good shield there and a tubing that has water that runs through it. So the heat that comes off heats this water. This water runs through a bigger thing of water, which then in turn heats this water, creating the steam that goes out and obviously is used for power. Obviously, they try to keep the nuclear part a little bit away from the main part there. This is why nuclear power plants are usually near big bodies of water, like they're off the 5 there in San Clemente, right? Although they're not really functioning, I think, anymore. But usually, a lot of times, they'll build it near a large body of water so they can kind of use that to cool everything down and keep the process going. If they're not near large bodies of water, they usually have pretty big cooling towers, or sometimes referred to, like in Arizona off to 10 there. They have big towers that are used to cool that nuclear power plant that's off there. So why does this fission reaction not go out of control? Where there's a couple of safeguards that they use, obviously, when they're doing some type of nuclear power plant, they keep the mass as subcritical. So they keep a subcritical mass of uranium or fissional sort of products. They also usually will have several control rods that are in the reaction sort of part of the chamber. Control rods are have cadmium or something like cadmium sort of on them, and they are actually really good at absorbing neutrons. And that would be good in this type of reaction because what kind of kicks off the reaction is neutrons. So you got these control rods that could kind of absorb a bunch of neutrons and kind of keep the reaction under control, along with a subcritical mass of uranium so it doesn't go out of control, right? So you don't have any type of meltdown or anything like that. Unless, of course, like perhaps in Chernobyl, you pull out too many control rods at once and you can't get them back in at the right time when you're doing a safety test or something like that. So that's not good. Um, so nuclear power plant uses this fission reaction to sort of heat the water. Traditional power plant, obviously said, uses coal. There's benefits and downside to both. Obviously, coal power plants usually will have a lot of byproducts as from burning coal, getting the coal and all that kind of stuff to do that. Now, nuclear power is cleaner in a sense that you don't get all that SO2 and CO2 problems, but you do have other sets of problems, like you create a ton of radioactive waste, which has long half-lives, like half-lives like none of us will see one of them, right? So what do you do with them? Where do you store it? People don't want it stored in certain places. So for the longest time, these nuclear power plants would actually just store everything there because nobody wanted this stuff trucked anywhere and stuff like that. I think now they have in Nevada, they dug a big hole and they put a lot of that stuff over there. It's how the neon lights stay, bright there in Vegas, man. But now they started shipping some of that stuff over there. By the way, a lot of nuclear power plants are been sort of decommissioned, if you will, not really used too much to keep them up to code. It's a lot of money. I think both in San Clemente, if I'm not mistaken, now are pretty much not too much in use anymore at all. So part of what is made in this nuclear fission reaction was sometimes referred to as spent fuel, and spent fuel is really the products of this fission reaction, and themselves have a pretty long half-life and storage time and are pretty radioactive and needs to be kept secure because you could do some bad things with those type of things and they stay around a really long time. As you can see here, these are some of the storage time for some of the spent fuel. And that's like 10 to the, 6 years or something like that. That's a lot of years to try to keep it stored. It's safe, and who guards it year after year. So benefits and downsides, obviously, to both. Um, any questions on power plants? Lastly here, nuclear fusion, which is a little bit different than fission. Fusion is really when we take two small nucleuses and kind of put them together at extremely hot temperatures, like the sun type temperatures. And that's really, really hot. So two smaller things make a larger sort of guy, gives off a lot of energy as well, and usually has to be done at really, really high temperatures. All the old spy movies where they always wanted the guy that created cold fusion, right? Where you could do it at kind of colder temperatures. They're all hunting that guy down. We also can use radioactivity a lot in medicine, and in terms of half-life, clearly, if you're using something with in medicine, you would want something with a very small sort of half-life. Here are some, and some of the things that you're used for: sodium 24. It's a blood flow tracer. Iodine 131 for thyroid. Um, Fluorine 18, positron emission. The nice thing about radioactive isotopes and those same elements in your body is they perform the same chemistries. So the benefit of the radioactive isotope, for example, on scans and stuff like that, is it could highlight obviously anywhere that sort of element is, and you'll be able to see what's going on with it. They also have used over the years, and I think still do, put radioactive sort of pellets and seeds and tumors and stuff like that to try to shrink them. And that's been used before as well. So a lot of imaging is done with radioactivity. Obviously, like I said, you definitely would want more of a small half-life there for your follow-up visit, not to be forever. Here's a bone scan there with technetium 99. You can see just sort of highlights all the areas on the scan. One very common thing that you use when you do work with radioactivity is a Geiger counter. Geiger counter has a cathode and anode, a little wand, and sort of kind of beeps as you move it around to radioactivity. Typically, if you use radioactivity, say in the laboratory or anything like that, usually a part of your cleanup, and as you're using it, go around everywhere else, make sure you didn't contaminate anything. Maybe check your shoes so you don't step on it or anything like that. If I take a Geiger counter, will it make noise if I just hold it up? It will. There's background radiation, right? It shouldn't be super loud, or you might be in some bad trouble. But there is going to be some background radiation that it always picks up. That's the other thing you commonly hear when people are using it. Don't worry, it's just background radiation. It's like beeping like no tomorrow. It's just background. Don't worry about it. So speaking of that, there is, like I said, it's just sort of background radiation for everything. And there is a RAD, which is a radiation absorbed dose, and a RAM, which is sort of the equivalent for man. And it does depend on the type of emitter. So as we saw earlier in the chapter, something like an alpha particle doesn't go as far into your tissue, which means maybe you could get shot with some alpha particles a little bit more than you could, say, gamma rays, which penetrate very deeply into tissue and stuff like that. So cosmic rays, 20 to 50, you get medical x-rays or dental x-rays, air travel. If you happen to live near a nuclear waste or fallout for weapons testing, you might get some of those type of things. So again, we do have obviously radiation around us. The key is obviously if you're ever working with it, as I mentioned before, you should always make sure that you understand the type of radioactivity you're dealing with, the type of emitter, and the type of protection that you need to protect yourself. Like I said, a lot of times they will give you a ring sometimes when you're working with radioactivity, a badge, and they would develop it after so much time to make sure you're not glowing, or those things are very much exposed, so you didn't get too much of a dose of those type of things. So a lot of times they'll use those type of things in the laboratory to try to keep you safe. Those are strawberries. It's lovely. It's good. Any questions on that there?